Testing. 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 Testing, testing. Testing, testing. Alrighty. Works. We're live. Alright, welcome to the last stream of the week. We're closing things off with some robotics. So, originally I was going to read this paper. So this is a paper called Galactic. This is a framework paper. So what do I mean by a framework paper? So sometimes papers are about a specific algorithmic contribution or maybe some state-of-the-art result. But other types of papers are more just explaining a new type of framework, aka just a bunch of code. And in this case, the code that they use at Meta to run their robots, right? So I like to read these papers not because this particular solution is going to necessarily continue, because in a year the framework will change. But I like to read these just to kind of see what people are doing, right? So, for example, here they're talking about the number of GPUs, the kind of where they use C++, where they use Python, like what type of cameras they're dealing with, and so on. So these are generally very informative because you can kind of learn a lot about what type of robotics and what type of projects they're doing and what the different requirements that they have. You know, like if they really care about speed, do they really care about memory? Do they really care about, you know, what do they care about? So that's the paper I was originally intending to read. But when I woke up this morning, I found out that DeepMind dropped a paper called Language to Rewards for Robotic Skill Synthesis, which is even, I think this is more important. So this one is probably more interesting from an algorithmic standpoint because they're actually doing very similar to what that Minecraft paper that we read, right? Where basically, if you remember in the Minecraft paper, which was called Voyager, the user request is fed into an LLM, and the LLM created a bunch of code that uses the Minecraft API. And basically, this seems to be a similar kind of approach where the user has a request, such as here, make robot dog stand up on 2 feet, and they have an LLM turn that request into specific calls to some robot API here. Right, so obviously these are Python functions, but they're probably wrapping kind of modular pieces of functionality that are usually written in C, because generally in robotics you want the low-level stuff to work in C because it's just significantly faster. So I was like, I have to read this, right? And then I'm kind of torn between, okay, well, do I read the original paper or do I read this new paper? And I think what I'm going to do is I'm going to read a little bit of both. So it's going to be kind of a weird back and forth here, but hopefully we can maybe go further by looking at both of these rather than looking at just one. So here you go. This is the robot at Google X. I have a video on this robot as well, but it's got a stereo camera up here on a pan tilt rotate mount. It's got this 7 degree of freedom arm with a pincer gripper at the end. You can see it has a little bit of compliance there, right? So this joint here, these finger joints are not articulated or not powered. They're basically just soft and compliant, and they just shape around the object. You got your little red E-stop here, so somebody can just hit it. The red E-stop is a little bit unnecessary because honestly, this arm is made out of plastic. It's not like a industrial robot arm at a car factory where you need an E-stop because it will literally rip your arm off. This arm is not the case. And then you have this little spinning sensor here, right? You see this? That's a a LiDAR sensor right there, and it's giving it a 3D point cloud of the world so you can see how it spins to get a full 360 view. Well, at least not behind it, but yeah. So let's maybe read the abstract for both, and then we'll go from there. So let's start with the original paper. We got Galactic, scaling end-to-end reinforcement learning for rearrangement at 100K steps per second. This is a couple different people. You got people from Georgia Tech, which actually has a pretty good robotics program, and then you got people from Meta AI. And I actually know this guy. I think this guy used to work for Unity. I've actually talked to him before. But, okay, let's see. We present Galactic, a large-scale, let me make this a little bit bigger for you guys, simulation and reinforcement learning framework. So simulation is key there, and generally the way that robotics is done, you basically do everything in simulation, and usually you have these frameworks where you basically want the simulation and the real world to be as similar as possible, right? Taking something that's been trained in simulation and deploying it in the real world, usually it's very difficult. So at this point, the frameworks that people use, for frameworks as in the actual code and the abstractions that are built into the logic that the robot executes, they actually build these frameworks such that they can very easily toggle between simulation and real world, right? To hopefully make that as painless as possible so that all the weird idiosyncrasies of the specific framework are duplicated in simulation and in the real world. Specifically a Fetch robot. So Fetch is a company or a startup that made robots actually very similar to this one, the Google robot. They look very similar to this one, but let me see if I can get a picture. Yeah, now they've pivoted and they do a bunch of like more like kind of generic palette type robots. So these are kind of more mobile bases, but the robot that they were really known for was this one, which is a mobile base. It's got a LiDAR there, and it's got an arm on it with the same parallel jaw gripper, and then the same kind of pan tilt yaw stereo camera up here. This is the original founder, Melanie Wise, but I don't even think she works for Fetch anymore. I think she left, and now she works somewhere else. Let me actually see. Melanie Wise? Yeah, so she's actually left Fetch and now joined Agility Robotics, which is the company behind this humanoid robot, Digit, if you guys have ever seen it. I think Digit is one of the more impressive humanoid robots. Here they are at a conference show, and you can see they have basic workflows like taking boxes and moving them and stuff like that. I think there's a lot of companies working on humanoid robotics, right? At least Tesla, Digit is there. There's one actually super close to my house called Apptronic. But Boston Dynamics, of course. But they don't really have demos to the point that this company does, Agility Robotics, right? It's one thing to have a 10-minute video like Boston Dynamics where everything is scripted and you have all these post editors that come in and choose the best things. And it's a totally different thing to have your robots running at a conference where anybody can film them with a cell phone camera and have them run for 8 hours straight. So when it comes to robotics, don't look at the smoke and mirrors, look at the actual complexity of the demos that they're showing you. And at least from what I've seen, Agility Robotics is one of the strongest contenders out there. So that's Agility Robotics, which is where Melanie Wise is now the CTO. Melanie Wise, who made the Fetch robot, which is the robot, this one here, which is the robot that they're using in this paper. Okay, equipped with a mobile base. So the mobile base is, of course, this part here, right? And they actually sell it separately as well. You can basically have just the bottom part or just the top part. 7 DOF arms. So DOF there stands for degree of freedom, and it basically means joint. So you see how you have twisting degrees of freedom. You have kind of more degrees of freedom like that. Rotating. So those are the different degrees of freedom there. You have 7. 7 is a very common number. And why is it a common number? It's because there's 6 you have X, Y, and Z, right? In our 3D space, you have 3 degrees of translation, and then you have 3 degrees of rotation. You have yaw, pitch, and roll, right? So in order to be able to put your end effector, which is a fancy name for the actual hand of the robot, right, the little gripper, in order to put it in an arbitrary 6 degree position, generally you need 1 more than that degree of freedom. So that's why 7 degrees of freedom is a very popular amount of degrees of freedom for robot arms. RGBT camera, so RGB is just a normal camera, and then the D at the end there means basically depth. So that's where the depth sensor would come in, right? So if you have a stereo camera, you have depth. You can also get explicit depth from LiDAR sensors like this one here, and then also there's generally a structured light sensor in the eyes. So it's basically projecting this infrared pattern, and then there's a camera that's usually black and white that looks at that infrared pattern and looks at the deformation of it, and then gives you a depth. Structured light, infrared. Let me see if I can find a good pic of this. Yeah, it kind of looks like this, to be honest. This is what you should think of, right? So usually you have your RGB camera, you have your infrared camera, and then you have your projector, which is projecting that pattern. And when it projects that pattern, right, it looks like this, right? So from the RGB camera, it doesn't look like anything, but the infrared camera can look and see that infrared pattern, and it can see the deformation of it and then give you this, which is the depth. So RGBD is a camera that gives you this and then gives you this. And generally there's a little bit of processing that you need to do in order to align this depth image to the color image, especially because the cameras aren't exactly the same, right? So you have the camera here, the RGB camera is generally not lined up exactly with the infrared camera. Yeah, RGBD sensors actually low-key suck, to be honest, though. Those structured light sensors are terrible because they're very, very sensitive to the ambient light. So how much lighting is there? If you have a structured light sensor and then you basically switch the lights on and then switch the lights off, it works very differently. And also it's very sensitive to the object itself. So a shiny object will react differently to a non-shiny object, an object that is black versus an object that is white, right? So like the color, the material of the object will actually have a huge effect on the depth. So very notoriously finicky sensors. Ego motion and onboard sensing. So the robot basically has some idea of like how much it's moved and what its speed is, right? And where the position of all the joints are, sometimes also called proprioception, right? So humans have this too, right? If you close your eyes and you move your arm like this, you kind of, in your head, have an idea of where your arm is, even though you're not looking at your arm. So you have an idea of where your joints are. Okay, is spawned in a home environment and asked to rearrange objects by navigating to an object, picking it up, navigating to a target location, and then placing the object at a location. So this is basically the episode. So in reinforcement learning, generally you're not playing a simulation or a game for hours at a time. Generally, you're basically doing it in these little chunks called episodes, and episodes, sometimes also called rollouts, are usually relatively short, maybe like 30 seconds, 10 seconds, something like that. And it just consists of a basic set of tasks, like go to object, pick it up, go to target, put the thing. And then as soon as you drop it in the bucket, it ends the episode, ends the basically game, and the system resets, right? And when you reset it, you respawn in a random part of the house. So this kind of pattern of like these very small little repeatable tasks, and then you basically spawn and do the task again, that's kind of par for the course for reinforcement learning that uses simulation. And that's one of the reasons why transferring this into the real world is difficult, because you can't spawn in the real world, right? If you have a robotic system in the real world, the reset is actually very expensive, you know. Once the robot places the object, now a human has to come in and move the robot back to the original position and put the object back in its original position and then reset everything and hit go again, right? And that process is very slow. In simulation, you can do that very, very fast, and you can do it in parallel across many different computers. So this kind of reset problem is one of the big problems with simulation and transferring these approaches into the real world. Galactic is fast. Okay, so speed is what they're going to be talking about here, I guess, or showcasing. In terms of simulation speed, rendering plus physics. So generally, simulations are built on top of similar technology to game engines, right? And game engines have loops for rendering. So in a game engine, there's a bunch of code known as shaders. It's not even worth pulling up a picture, but there's a bunch of code that basically calculates what an object looks like based on material properties and the way that the light is bouncing and so on. And that's a whole kind of mess of computation that you need to do. But then there's also a bunch of other computation that is actually the physics, which is, okay, now you have these objects, and these objects usually have colliders, right? Colliders are primitive versions of the object, so maybe something like this, right? If you have this gun in a video game, you have the actual mesh, but then you have this second mesh known as the collider, which is basically whenever you have to do these physics calculations, you're doing a lot of intersections. So you're basically constantly checking to see if objects are overlapping with other objects, and then if they overlap, based on how much they overlap, you can assume that that's some kind of force, and then you basically are constantly calculating these forces and these overlaps and acceleration associated with that, and it's very expensive to do that, and especially if your collision geometry is very advanced. So here, for example, you have two different collision geometries here. You have this one, which is much simpler, and then this one, which is much more complicated. So complicated collision geometry explodes the amount of computation you need to do when it comes to the actual physics. So people have basically tended to use very simple collision geometry, which is why sometimes whenever you see in a video game the way that an object interacts with the environment, the collision geometry doesn't perfectly match the object. Okay, so that's what rendering and physics are. There's a lot of trade-offs there, but there's probably some tricks that they do in this paper in order to improve those. Galactic achieves over 421,000 steps per second. Really missed the opportunity to make it 420,000 steps per second on an 8 GPU node. Okay, so we got 421,000 steps per second. Actually, the color for that should be blue. And then we got an 8 GPU node. So as soon as you see 8 GPUs, that's a server rack, right? So GPUs, everyone's familiar with the GPUs in your house, but generally having more than 2 or 3 or 4 GPUs in your house is very difficult in one kind of motherboard, like a consumer motherboard. 8 GPUs is a very standard number for a server rack, which is what most of these people use. 54 times faster than Habitat. So Habitat is another robotic framework simulation environment that Meta AI released. It's actually quite old at this point. Let's see what the original paper is. Yeah, maybe 2020. I think it's older than that. I feel like I've seen it before. But so this is the new version of it. And it's interesting to note that there was Habitat 1.0, then there was Habitat 2.0, and then rather than this being Habitat 3.0, it's Galactic. So that tells you something, right? Because whenever you design a framework, right, for simulation and reinforcement learning, there's some design requirements about, okay, well, what is this framework going to do? What is important? What are the different robots and maybe collision physics rendering that we're going to have as part of this framework? And those design requirements, once you put them there in a software system, it's very difficult to change them, right? So there's this kind of inherent property of software that you decide on some design requirements, then you build those into your system, and then it's very difficult to change them in previously. So whenever I see that they went from Habitat 1.0 to Habitat 2.0, and then they decided to do something entirely new here called Galactic, that tells me that the requirements changed. something changed here. Something between Habitat 2.0 and Galactic, the requirements changed. So what requirements changed? And I think if I had to guess, probably related to LLMs. So Habitat 2.0 probably absolutely zero kind of functionality or abstractions that would enable LLMs in the loop, right? Like this paper here, right? LLMs in the loop are kind of becoming the new way of doing reinforcement learning, right? Versus Habitat 2.0 was probably based around the idea of the partially observable Markov decision process, and then you have something like a PPO running on top of that. So Habitat 2.0 is like old reinforcement learning, which actually used to be new reinforcement learning, right? There's an even older type of reinforcement learning, but old reinforcement learning at this point is basically known as deep reinforcement learning. And I think we're actually in a phase transition right now where deep reinforcement learning is being replaced by LLM learning, or whatever you want to call it, where basically we're using these LLMs as basically the agent in the environment. So that would be my guess, but it could also be related to firing people. So I know that Facebook and Meta went through a huge amount of firing and kind of restructuring, so that could be another reason why they decided to build a framework from scratch. Okay, so Galactic was designed to optimize the entire rendering, physics, and reinforcement learning interplay, since any bottleneck in the interplay slows down training. Any bottleneck in the interplay slows down training. Yeah, okay, so seems like software 101. If you have any kind of software system, right, the whole point of profiling a software system is to find the slowest parts, and then generally if you fix the slowest parts, that's the best way to make any software system faster. So I guess that's kind of what they're suggesting there. In terms of simulation plus RL speed, rendering plus physics plus inference plus learning. So these are all computational costs, right? You have to render the environment. You have to actually generate an image based on light bouncing and knowing what objects are there. You actually have to calculate the physics at every single step, right? You have to know, okay, how much are these objects going to be moving because of their intersection and their interactions. Then you have to actually do the inference. So you actually have to push some sensory observation, some combination of a camera and some state in through some kind of neural net. Or the inference could also be this, right? You actually have to run a LLM for some amount of time. And then you actually have the learning cost, which is, okay, I gathered the actions that I took and the observations that I had, and now I need to basically push gradients or adjust some kind of parameters as a result of that. So these are kind of the four main computational buckets that you have in reinforcement learning and simulation. Galactic achieved over 108,000 SPS. I mean, this is kind of weird. Why is it 421,000 SPS and then 108,000 SPS? They literally give us two numbers for the same thing. That's weird. These massive speedups not only drastically cut the wall clock training time of existing experiments, but also unlock an unprecedented scale of new experiments. Yeah, so I mean, if you can do simulation faster, right? If you can make this game, basically this game and this inference and learning and this whole pipeline faster, then you can also basically do more and more experiments. First, Galactic can train a mobile pick skill. A pick skill is the ability to pick an object, right? So basically this, grabbing an object, that's a pick skill right there. And then a mobile pick skill is whenever you're not in front of the object. So most of the time when people do robotic picking, the object is like right in front of the robot. So it's all you have to do is just move your arm and grab it. But a mobile pick skill is whenever you actually, the robot might not even start next to the object. So it has to move a little bit and then grab it. Greater than 80% accuracy in under 16 minutes. So I mean, this number, very difficult to judge because you have no idea how difficult the mobile pick skill is, and you have no idea what 16 minutes means, right? Like, did they start from a pre-trained model? Did they just train it from scratch? Like, what does from scratch mean? So don't read too much into this number. We use Galactic to perform the largest scale experiment to date for rearranging using 5 billion steps of experience in 46 hours. So 5 billion steps of experience. Each step is basically one frame of your simulation. So probably one picture, a bunch of observations, and then one action. So kind of like a Markov decision process, right? It's the entire simulation is discretized into these steps, and then here they're telling you they have 5 billion steps in 46 hours. This scaling results in a single neural network composed of task-agnostic components, achieving 85% success in geometric goal rearrangement. So this is probably the task that they're describing up here, where you basically have to move things from one place to another, and so on. And then you have the actual code base right here. Facebook Research, Galactic. Let's see what license they have. Attribution, non-commercial. Okay, so attribution is it means that if you use this work, you have to attribute it to them. So you have to basically reference them. You have to say, hey, I'm using this Galactic from Facebook Research. And then non-commercial means that you're not allowed to make money from it. So you can't make a humanoid robotic startup and then use the Galactic. You can only do this if you're a researcher, and you have to tell them. So you have to attribute, you have to cite. Cool, let's maybe scroll through here. What do we got? So first thing you see here, this is the installation instructions, right? They're cloning a GitHub repo, going into that folder, creating a Conda environment. So as soon as you see a Conda, that means Python, right? If you create a Python environment like that. But you see here how they also have CMake. CMake is what you use to build C++ code, right? C++ is a compiled language, which means that you can't just run it. You have to compile it first. And when you compile it, what really is happening is the computer is going and is looking at your C++ code, and it turns it into this executable file. And it basically looks at your code and says, okay, here's what you wrote, and then here I'm going to basically write a version of that in a language that you can't really understand, right? Which is the compiled code, right? The machine can understand it, but it's very difficult for you as a human to understand it. And that code is going to run much faster than what you wrote. Python is not compiled, right? So that's why Python is so much slower than a compiled language like C, because it doesn't go through this process of being compiled into a much faster, more efficient code at the trade-off of being basically less readable, because now only the computer can really understand that. Okay, so creating a Conda environment, activating that Conda environment. Vulkan is a series of graphics. You can think of it kind of like NVIDIA, but for Linux. That's one way I think about it. If you want to play games on Linux, generally you end up using this. Cross-platform 3D graphics, collection of tools for developing and debugging Vulkan. Low overhead cross-platform API for 3D graphics and computing. Some people like it because you don't have to basically rely on external things. A lot of times graphics stuff is potentially expensive or proprietary, but I just feel like Vulkan is just gross. Every time I've tried to mess with Vulkan, it just ends up being this giant tangle of dependency hell, and it doesn't work, and it's very annoying. So I don't know, I generally don't like it, but it seems like they use it here, right? So you can see they get a specific version of Vulkan here for Linux, right? x86 architecture. They tar it, which basically means they unzip it, and then they run this script that's inside there. Install and verify PyTorch with CUDA 11. This is an older version of CUDA, so it makes me, yeah, look at this. CUDA 11.7, PyTorch 1.1.1. So that's not a very modern version at all. They're definitely using some old shit there. Here they're just printing that, make sure it works. Unzip. URDF is a ROS concept. So a URDF is a file unified robotic description format. It's basically a I think this is a good thing here. Yeah, so basically, when you have a robot, right, you can think of a robot as a series of links and joints, right? So remember how we said 7 degrees of freedom? Well, each of those degrees of freedom is basically one of these joints. And joints tend to have basically similar properties, right? They have some speed, they have some minimum position, some maximum position. Links have some minimum, some maximum. So whenever people created ROS, which is the robotic operating system, an open source robot kind of framework that people made, it became important to have a unified way of describing robots for that framework, and that's where URDF came in, right? So URDF is basically think of it like a JSON file, but it's used to describe robotic systems, especially popular with ROS. Okay. So they have a URDF for the robot. What else do they have here? So here they're actually building. So you can see they're building the Habitat Sim Python module. So this is kind of interesting, right? It's Habitat 2.0 and then Galactic, and then Galactic instructions include building Habitat Sim. So maybe this really should be Habitat 3.0 and they just called it Galactic to try to be fancy. Okay, and then you basically install, build, and then run. Okay. So we got some idea of what they're doing there. Yeah, it really seems like they're using Habitat a lot, so maybe this is not what I thought it was. I thought it might have been something new, but it sounds like it's maybe Habitat 3.0, and all they did was just rebrand it as Galactic to make it seem like it's something different. Okay. So let's see what they have in this table. High-level throughput comparison of different simulators. Steps per second are taken from source publications and don't control for all performance-critical variables, including scene complexity and policy architecture. Right, so if you have a very complex scene, right, that's going to make the rendering and the physics very slow. If you have a very complicated policy, right, that's going to make the inference and the learning slow. So policy is just another word for an agent, which is another word for the actual neural net or system of neural nets that you're using to determine what action to take. It's just a word that comes from the reinforcement learning terminology. Comparison should focus on orders of magnitude. We show sim SPS, so simulation steps per second, which is basically physics and rendering, and then training SPS, which is inference and learning. I guess they combine them, so inference and learning and physics and rendering are training SPS. VizDoom arcade simulator as a classic benchmark, 80 times faster, blah, blah, blah. Okay, let's see these actual numbers here. So you have VizDoom running on one RTX 3090 at a resolution of 28 by 72, which that is very tiny. That's like a little thumbnail picture. It's not photoreal, and it kind of only has primitive physics, I guess is what they mean here. And you get 38,000 sim steps per second. Isaac Jim, this shadow hand is pretty cool if you guys have ever seen this. I actually got to work with this robot when I was at Google, but it's basically a very, very fancy articulated robotic hand, right? It has, I think, 21 different degrees of freedom, which is pretty crazy. But what they won't tell you is that this hand is extremely fragile. So one thing that I immediately ran into when I was playing with this robot is that if you run this thing for more than like an hour, it'll snap one of the tendons. So there's basically these tendons that go all the way through the hand. And the problem is that as soon as you snap one of these tendons, you have to basically take apart this whole bottom part here. And this bottom part is very, very tight. It's like, it almost feels like you're like you know how like whenever you watch like a video of a guy who like undoes a clock, they're using all these little tiny tools, and they're using like a little binocular just to take apart this clock because it's this giant mess of like gears and things that are all right on top of each other. The inside of this wrist looks exactly like that. It's basically this giant clockwork of screws and gears and crap, and just fixing one of these cables takes like 8 hours. No joke, because you have to take everything apart and then put it all back together and then run all these tests. So I don't know. TLDR, my experience with the Shadow Hand is that it's a bunch of garbage. But Isaac Jim is the simulation framework for the Shadow Hand. Gibson, AI to Thor, Megaverse, LBS, these are just different. Embodied AI, EAI means embodied AI, and that's just a fancy way of saying AI that's inside some kind of body, right? So the body in this case would be a simulated robot. A couple different GPUs. This is kind of a terrible chart because, I mean, like, this is a vast difference. There's a huge difference between one RTX 2080 and then one A100 and 4 TPU pods. And I also disagree with this. Photorealism is not a binary yes or no. Photorealism is a spectrum, and this does not feel like photorealism. You know, like, there's a big difference between this and Unreal Engine like 5, you know, so I don't think this is photoreal. So maybe a negative there as well. You know, where they're like, oh, this is photoreal and this is not photoreal. No, I think photorealism is a scale. It's a continuum. So I don't like this checks and X's. Okay, so let's kind of scroll through here, see if we can find the part that I'm looking for. So I don't really care about related work or any of this crap here. What I want to see is this. I want to see them explain the actual system, so we're going to skip to section 3 here directly, which is where they describe the system. From an ML systems perspective, RL training can be broken down into a rollout computation. So rollout is another word for an episode, which is basically another word for one session of the game, if you could think of it that way. Collecting experience. Experience is basically just data that is related to a specific simulation, right? So embodied AI collects experience. And like, this is kind of one of the things that I find annoying about robotics is that like the terminology is different, but the thing you're doing is the same, right? So like if you come from an NLP background or a computer vision background, you know what all of these are, right? You actually intuitively have very good ideas of what's going on here. You just don't recognize the terminology because the terminology comes from a different kind of historical legacy, right? It comes from the historical legacy of reinforcement learning and robotics. So collecting experience is just another way of saying like you have a data set. You have data sets for supervised learning that have a action and a reward and a observation. And learning, updating the policy, right? So another, again, updating the policy, you might be like, I don't know what that is, but that literally just means pushing gradients into a neural net, and that neural net is deciding what actions to take. Our system contributions focus on speeding up the experience collection, so making the simulator faster. We optimize batch rollout. So whenever you have these simulated systems, right, usually you're not collecting experience at like one sequentially. So it's not like you have the robot plays the game and then it ends and then it plays the game and then it ends and then it plays the game. You're doing it in a batch, right? You have lots of GPUs all batching these operations at the same time. So you can basically collect 20 years of experience in whatever, 1 hour. Computation for a single GPU and associated CPU process. So one thing that's popular in these simulation frameworks is that generally you use the CPU for the actual simulation and then the GPU to actually do the graphics and then the neural net part of it, right? So for example here, the CPU or the physics is being done in with the CPU and then the rendering is being done with the GPU. DNN inference, this is just deep neural network, which is just neural network. Introducing a new approximate kinematic simulation optimized for EAI or rearrangement tasks. this makes me think like they have done something with the physics. So there's different physics engines that you can use. There's, for example, PyBullet, and there's also Mujoko. This is a physics library, right? So physics engine is basically just a bunch of code that someone wrote where you can calculate the forces and the acceleration and the velocity and primitive things like friction as well, even though friction is not very well modeled. Another very popular kind of physics engine. Mujoko is not just a physics engine, it's more like a higher level thing, but Mujoko is known for its very good physics. I've used this before. I don't like Mujoko for other reasons, but it actually has very good deformable physics. Like you can do like ropes and tendons and stuff like that. So Mujoko is also very popular for robotics. For our RL experiences, we combine fast rollout with DDPO. PPO is a very common reinforcement learning algorithm. I think it's proximal policy optimization. Let me make sure I have that acronym correct. PPO-RL. Proximal policy optimization. This is one of the most generic and simple reinforcement learning algorithms. And then the DDPPO here is deep distributed PPO. So PPO using a deep neural network and distributed over a large computation mesh, if you want to think of it that way. But this is not good, right? As soon as I see this, what this is telling me is that this paper isn't doing this, right? This paper is not doing the modern reinforcement learning, this 2023 reinforcement learning where you're actually using an LLM inside the loop as the policy, potentially generating code, right? Which we saw in the Voyager paper. As soon as they mention DDPO, I'm like, okay, these guys aren't doing LLM-based reinforcement learning. What they're doing is 2015 reinforcement learning, which is basically just taking PPO, which is an algorithm from the even older type of reinforcement learning, and then putting a deep neural network on top. And this type of reinforcement learning, this deep reinforcement learning, doesn't work. It works well enough for demos and papers, but there's a reason we haven't seen humanoid robots in 5 years ago, right? I think that humanoid robots are going to come from this. They're going to come from the LLM-based reinforcement learning. Okay, so that's a little bit sad. Batching. Consider non-batched EAI simulators. So non-batched basically means that it's just running one rollout at a time. One Python process, one simulator, one environment. So they're kind of shitting on the fact that Python, not only is it not compiled, but it's also runs basically one thread at a time. There is ways to do multiprocessing and multi-threading in Python, and now you have async as well. So there has been progress that is done on that, but generally Python code runs with what is known as the global interpreter lock, which is this abstraction that prevents basically, or that everything has to go through this lock. And what that means is that it makes Python very easy to debug because you can step through it, right? You don't have multiple things that could be running at the same time, and that depending on the order in which they run, you could get weird bugs, right? Which is the hardest part about debugging, threading, or multiprocessing applications like that, is that the timing matters. But because Python has this global interpreter lock, the timing doesn't matter. You can basically perfectly stop time and then step through it one by one and then resume time. And that's why Python is easy to debug, but it's also very, very slow because of that. So what they're talking about here is that if you have a embodied AI or system that has Python in the loop, which usually was the case because these DDPPO and these deep neural networks that they use for the policy are generally written in physics or in Python. So in these simulators, you have Python in the loop, which means it's very hard to have a batched version of that because the Python needs to run with the global interpreter lock, and thus it's inherently kind of single-threaded. Yeah, some task-specific logic is implemented directly in Python, such as extracting a robot pose and computing reward and so on. And as soon as you have any part of your system that's written in Python, it's all going to be as slow as that Python code. So sometimes what people do is they'll they'll get rid of all the Python code. They'll basically take that Python code, turn it into C++ code, and then run only a pure C-based simulator and simulation and experience collecting loop. But that's expensive to do, right? Because now these are generally different types of people, right? The type of person who writes all the Python code and comes up with kind of the concept and the actual MVP is going to be different from the type of person that can implement a bunch of really, really fast and efficient C++ code. So you have this kind of fundamental problem that people who are good at Python are generally not great at C. And I'm one of those people. I'm definitely much more of a Python person than a C person. To scale this RL training, these approaches typically spawn multiple Python env processes. Yeah, so generally you're basically relying on your CPU, the fact that you have multiple CPUs in your computer, and you're basically spawning. It's like almost like if you were to run a Python script multiple times, like open up a terminal, run a Python script, open up a new terminal, run that same Python script. Now you're running two of those Python scripts at the same time. Each of them has their own global interpreter lock. So in a sense, now it's faster because they're both running at the same time, but that's not necessarily great either. In-memory assets include CPU data, physics, collision geometry, GPU data, meshes, and textures, right? So the GPU is what's doing the rendering, and in order to do the rendering, you need meshes and textures. So people talk about GPU memory all the time for training purposes, and whenever you're training a neural net, right, the stuff that's actually inside your GPU VRAM is the weights of the neural net, and then the batch that you're putting into your training, right? But whenever you're using a GPU to simulate and play a video game, what's in the VRAM, right? Well, it's the meshes and the textures. That's what's in there. So the bigger your GPU VRAM, the more complicated and the more high quality the textures and the scenes can be, the more your mesh can be, and so on. CPU does all the physics generally, so they must be duplicated across instances, not shared. Yeah, so if you have multiple Python processes that are each doing something like this, right, they don't share memory, right? So if you just run two Python processes separately, there's no way to have them share the same memory. And that's the most complicated thing about multi-threading is basically memory sharing, right? And generally you have to have these abstractions known as locks, where you basically lock a specific chunk of memory, and it can only be accessed and rewritten by one process at a time or one thread at a time. So that duplication that happens when you run these multiple Python processes is not optimal. Observations are batched, fed to GPU-based batched DNN inference. Yeah, sometimes people have these pretty fancy setups where they basically have the actual, the computers that run the simulation are different from the computers that are doing the policy inference or the neural net inference or the actual AI that's in the embodied AI. Sometimes they'll separate those out because you have different requirements for the hardware, so having slightly different hardware that's optimized for running simulations in parallel versus having hardware that's specialized for calculating a bunch of inference. So I've seen fancy setups where people have different computers for that, but that anytime you add complexity like that, it just makes it very difficult for extending and making it better, right? There's kind of a limit of complexity that a team of software engineers can handle before the overhead just gets too much. Prior work has shown the benefit of batch simulation over this non-batched paradigm, both for CPU-based physics, GPU-based physics simulation, GPU-based rendering. For Galactic, we batch both CPU-based physics and GPU-based rendering. Okay, so this is kind of painting a story that makes sense, right? So I remember this guy worked at Unity. So this guy definitely knows his game engines, right? So you have a guy who knows game engines being hired into Meta. Then you have here Habitat 2.0, but then you look at the code and it's really, this feels like Habitat 3.0. And then not only does it kind of feel like Habitat 3.0, but then we scroll down here and we find out that they're not even using LLMs. They're using DDPPO, which is old school reinforcement learning. Old school, like by old school, I mean like 2015, 2016 reinforcement learning. So it kind of seems like all they did was they took Habitat 2.0 and then they got a guy from Unity to come in and just implement a faster version of batched physics and rendering. So that's kind of the story that I'm starting to read from this. For physics, the main Python process hosts a single C++ simulator instance. Okay, so you have a Python process that's basically communicating with the actual simulation, which is of course written entirely in C. This instance steps physics for a batch of environments, sharing in-memory CPU assets across environments. So you have a batch of environments, right? A batch of, in this case, I think they're rooms, right? Little rooms like this. And rather than having a bunch of simulations or a bunch of processes of this simulation and then having this texture of the floor, for example, duplicated across however many of those simulations, you have batched simulations. And inside those batched simulations, all of them are using the same exact memory location for example, the texture of this floor, right? So that works as long as every single simulation has the same exact textures and meshes, right? As soon as your simulations have different textures and meshes, you're not going to get any benefit from sharing these in-memory assets. So that's another thing to note there. And that's something that I think is more common than you think, right? You might think that, oh, well, it doesn't matter because your robot is all just doing rollouts in this environment. But actually, one of the ways that you get around the sim-to-real domain gap is by using a domain randomization, which is basically the process of changing the meshes and the textures of these objects to slightly different versions of them so that your robot becomes more robust to the exact visual appearance of it. So the problem with that is that if you're going to have 10 different floor textures, then that's 10 different floor textures, and you can no longer actually save it, or you can no longer save and share memory you can no longer save memory by sharing memory. Okay. Unlike 48, which moves nearly all task logic to C++, we retain the flexibility of Python for reward and other task-specific computation. So why is flexibility important for reward and task-specific computation? Because this particular generation of reinforcement learning, right, what I'm calling 2015 reinforcement learning, these PPOs, DDPPOs, A3C, like things like that, they don't really work super well. And a lot of what you end up doing is what's called kind of unfortunately reward shaping, which is where you're basically sitting around making different reward functions. You can think of the reward kind of like the loss function. So if you remember in yesterday's paper, the loss function was made up of the actual main loss, but then there was these extra regularization terms that minimize hyperspherical energy. So in a reward function, you have a similar kind of dynamic where you might have a main reward, but then you have this kind of long tail of weird other rewards that people put in, right? So what does this look like? Reward for Dota 2 OpenAI. Yeah, so this is the OpenAI 5. Let's actually look at the reward. This is the paper where OpenAI got one of what I'm calling old school reinforcement learning systems to do play Dota, right? And it's extremely over-engineered. This thing is very, very complicated. But for example, here, this is what I mean by reward shaping. Look at how complicated this reward signal is. You have a reward of 5 for winning, -1 for dying, 0.002 for XP gained, 0.006 for gold spent, 2 for health. Like, this is incredibly complicated, right? And some human designed this, right? So whenever here they're talking about the flexibility of Python for reward, it's because there's a bunch of people working on this project that their entire purpose is they go in every single week and then they adjust these numbers, they change the thing, they add more things here, remove certain things. And in order to be able to constantly change the reward and the way that the reward interacts with the actual robot and the observations, all of that, you basically need to have Python for that, because every single one of those is a code change, and if a code change in Python is way easier to do than a code change in C. Reward shaping is basically a bunch of if-else stacks. It's not literally if-else stacks. Reward shaping is more this process of using your human intuition and then iteratively changing the nature of the reward function over time as the project continues. But yeah, you can kind of think of it like if-else, but the if-elses are running in your brain. This is implemented as efficient NumPy tensor operations. So NumPy, there's a book that I worked through that I think might be worth it, but NumPy is the basically matrix package for Python, but you can vectorize code with NumPy. Let me see. Yeah. Maybe this is what I'm looking for. But yeah, so a lot of times when you write Python code, you can actually write the same exact code in NumPy, which is also Python, and it'll be way faster, right? Yeah, so for example here, like this is some kind of list comprehension here that you're doing manually in Python. But if you were to turn that into an actual NumPy, here it's explicitly kind of almost being compiled, if you want to think of it that way, with the vectorize. But there's a lot of times when if you're doing something in Python, you can think about it slightly differently, rewrite it all in terms of matrices in NumPy, and then it'll be much faster. So that's what they're talking about here, efficient NumPy tensor operations. In contrast to the non-tensor Python code in the non-batch paradigm. But I think what they're kind of not telling you here is that generally these kind of more efficient NumPy vectorized logic is more difficult to understand. So like one of the biggest benefits of Python is that non-tensorized Python code is extremely easy to understand, right? You can hire some new person and they come in and they look at the code once and they have a pretty good idea about what's going on, and they can change it pretty quickly. They can give you a diff in a day. When you have these kind of complicated, like vectorized, like NumPy operations, that's more difficult to understand, right? At that point, it's difficult to implement changes. If you hire someone and they come and you tell them to change something, they're not going to be able to do it as easily, right? So there's constantly this kind of struggle between the simplicity and readability of Python and the speed and efficiency of C++, and NumPy's maybe somewhere in between there. BPS renderer, scene graph, PyTorch, GPU-based batch inference. Okay, so this is kind of cool. So obviously you have your GPU is calculating your rendering, right? So it has all your meshes and your textures, and it's actually calculating what the picture looks like. And then rather than taking that rendered version of your video game and passing it to the CPU and then to the memory, and then that goes into some other GPU where you're actually doing your neural network inference, it sounds like here they're basically preventing it from leaving the GPU, so that it just basically they're all on the same thing. You don't have to wait for that to get passed around. This is kind of weird though, because what it means is that your GPU memory needs to not only contain your neural net, but it also needs to contain the images, and it also needs to contain all the meshes and textures. So this might be limiting their approach to very big GPUs, which is kind of what you see here. Tesla V100s. How much do these have? Tesla V100 memory. Okay, so 32 gigs. That's probably fine. So when you do this kind of approach that they describe here, right, where you basically don't pass the image through the CPU, that means that you have to fit all of that on one GPU. You have to fit your neural network, you have to fit your images, and you also have to fit all the meshes and textures. So the reason that this sometimes works is because sometimes the neural networks that they use for this are actually quite small, right? They're using these little tiny MLPs, little feed-forward neural networks, so it's fine. But if you tried to fit a big transformer into that, it would just not work, right? So, I don't know, that's not necessarily good that they're doing that. Integration of batch physics, batch rendering, and PyTorch DNN inference to the rollout computation loop. CPU-based physics is computed in parallel with GPU-based heavy rendering. Okay, rollout timeline for a single batch step showing our integration of batch physics, orange, batch rendering, purple, and PyTorch DNN inference, blue. CPU-based physics is computed in parallel with GPU-heavy rendering and inference. Okay, so here you have, I guess this is just one computer that they're showing you here, and you have your main thread, so this is basically your CPUs, right? The CPUs in your computer. The physics thread, so this is a different CPU in your computer, so you have some CPUs that are working on this, and then you have some CPUs that are just working on this. So two separate processes here. And then you have your GPU. So your GPU is basically alternating between running inference, right, which is the actual pushing an observation through the neural net and then getting some kind of action. And then it's alternating between that and then the actual rendering of the environment. So this is actually taking the meshes and the textures and doing all the light bounces and all the shaders in order to get the exact appearance, like this image, for example. But here there's a little gap, right? There's a gap where it's idle. And that idle is here, which is going to be loading. So actually what probably happens here is that you have your neural net, and then the neural net does inference, but then in between here and here, you need to get rid of all the intermediate, all the stuff in your GPU memory related to the deep neural net, and then put in all the meshes and textures. So this render setup, it's taking up CPU because it's probably loading the meshes and textures into the GPU, and then it runs the GPU. Okay. So, okay. Let me take this back. So here I was saying you're going to need to have all three of these on the memory, on the GPU memory. You're going to need to have the neural net, you're going to need to have the meshes and the textures, right, for the GPU rendering, and then you're going to need to have the images. And I was like, okay, well, that's a lot of stuff to fit on your GPU, right? Like, how are you going to fit all of that in your GPU? You're going to actually have to have something, right? And here's the answer. The answer is they're not actually fitting all of those on the GPU. What they're doing is they have the neural net, then they throw away the neural net. They don't throw away the neural net, but then they load the meshes and the textures. They render with the meshes and the textures. And then here, you see how there's no gap in between here and here because this generates the images, and then the images are just directly fed into the thing. But then there's going to be another gap there. So they have this idle period where they have to load the meshes and the textures, which is kind of annoying. Step post-processing, this is all the reward stuff that they're talking about here, this like Python code, right? So after you take your step in the environment, you get your reward from the environment, and this is calculated here in the main CPU thread. And then once you get all of that, then now you actually need to step the simulation forward. Okay, so here's the image that I got, here's the action that the robot's going to take, right? And the robot's basically frozen in time, and then we're going to move one step forward, so the robot moves, and then now you have to recalculate all the collisions. You have to look at your URDF that has your collision meshes. You have to basically recalculate all the intersections, recalculate all the forces, recalculate all the velocities and accelerations, and then that's what this step physics is, right? And you can see how they overlap that a little bit with the PyTorch inference. So by having the physics run in a separate thread from the main thread, you can get some saving here with the overlap, right? If you had the physics running in the same thread as here, this would have to wait until the end of this. Physics is fast enough for rollout computation to be primarily GPU bound. Okay, so they're saying that the slowest link in this entire system is the GPU itself. But I think if you actually looked deeper into this, it's not the way that they're saying this. This almost suggests that the GPU computation is actually what is limiting this, but it's not. I think if you actually inspected this deeper, what you would find is that it's communication overhead within the GPU. And this is a trend that's happening all over the industry, where basically GPU utilization is actually lower than it could be, right? Your GPU cores, the actual cores in your GPU that do the matrix multiplies, those are actually way faster, and what's slow is actually having to load things into the GPU memory and load things out of the GPU memory into the GPU memory, out of the GPU memory. So I suspect that that's what's happening here as well, is that most of the GPU time is actually just sitting there idle waiting for things to come in. Okay, approximate kinematic solutions. Physics realism, simple cylinder, right? So they're kind of just talking about how these colliders tend to be basically very simple shapes, right? Most of the time it's something like this. It's called a capsule, but it's basically like a little cylinder, right? So like you approximate objects with these simple collision meshes, so then your physics is actually kind of low-key shit. They're using the PyBullet, okay. What else? I'm scrolling through here. Collision geometry is used inside a physics simulator to perform the contact and overlap test. This is the overlapping of the collision geometry that I'm talking about. Sub-centimeter tolerances. Yeah, so in any kind of physics simulation, you also have this kind of trade-off of the finer the resolution, the more complicated the collision meshes, the longer it's going to take to query. So generally people have simplifications and approximations, but those simplifications and approximations are the reason that physics in simulated worlds are not as good as physics, or are not going to transfer well to physics in the real world. And that becomes this whole other field of research that people have done, where basically they use domain randomization in the space of physics simulation, such that when you're learning policies, you learn them with a variety of different physics environment or physics kind of settings. So maybe you change the gravity. Maybe rather than gravity being a specific value, the value for gravities has a normal distribution over some range of specific values, and then your robot gets a little bit more robust to the physics changing, which will increase the generalizability and the ability for the robot to jump over that sim to real gap. Geometric goal rearrangement task. Okay. Implement our simulator in C. It runs on the CPU in contrast to recent GPU-based physics simulators. So there are people who have tried to do the physics simulation in the GPU in order to make it faster, but I think the problem with that is kind of what you're getting here, is that everyone wants to use the GPU, right? The neural net wants to use the GPU for inference, the rendering wants to use the GPU to generate the images, and the physics could also use the GPU, and there's people who have done GPU accelerated physics, but then you have like everything is running on your GPU, and now that's going to be a bottleneck. So running the physics on a CPU, of which your computer has plenty of CPUs that are kind of just sitting there idle, so, or CPU cores, sorry. But yeah, so I kind of agree with this, that you're probably okay, or better off using the CPU for physics. Okay. Let's see if there's anything else. I'm like kind of just scrolling through here. Architecture and hyperparameters. Yeah, this is very, I think sad maybe isn't the right word, but just like kind of unfortunate. But like, I mean, look at this. ResNet 18 as a visual encoder, a 2-layer 512 hidden unit LSTM. Like, come on, this is literally ancient technology at this point. You know what I'm saying? Like, ResNet 18, like, you got to be using a VIT, a 2-layer 512 hidden unit LSTM. Like, you got to be using, like, you know what I'm saying? They're not even using transformers. These are ancient architectures and an ancient reinforcement learning algorithm, right? Compare that to this paper here. Like, this is, you want to be using LLMs, dude. You want to be using VITs for your vision encoders. Like, this almost makes me want to stop reading this paper because this is just fucking gross. Like, look at this. They're like simple CNN versus ResNet. Like, all three of these are shit, dude. Like, why are you still using a CNN? Okay. Let's read the conclusion. So we kind of skipped through the results, and now let's just kind of read the conclusion, and then we'll end this paper there. We propose Galactic, a framework for rendering physics and RL training for embodied tasks at a massive scale. To achieve high throughput, we develop an approximate kinematic simulator. So this is the CPU-based physics. It seems like it's kind of the main thing that they did here. That has a batch processing approach to jointly render the observations and simulate the physics. Learning mobile picking skills in less than 16 minutes. Okay. No one's going to use this. So a little bit of copium here, but you know, they're like, oh, we're going to enable large-scale training. All right, well, if you're going to enable large-scale training, I don't think having a attribution non-commercial license is going to help you, and I also don't think that designing your system around these ancient reinforcement learning kind of paradigms is going to help you at all, right? So, unfortunate, but, you know, I kind of like to read these papers, just skim through them just to see where the things are at and what people are using. But it's always good to kind of remind yourself of the different systems and how they do it. But all right, let's throw all of that away and let's actually go here into some actual modern reinforcement learning. And this is a paper coming out of DeepMind, literally came out this morning. So let's actually open up the actual paper. Language to rewards for robotic skill synthesis. Got a whole squad of people here. Oh, they even have a, no, that's just the GitHub. Demonstrated exciting progress in acquiring diverse new capabilities, ranging from logical researching to code writing. Robotics researchers have also explored using LLMs to advance capabilities for robotic control. Yeah, and this is kind of what I'm talking about. Like, to me, this is modern reinforcement learning. Like, there's like that Voyager paper from the Minecraft. There's more and more of these papers that are coming out where they're basically just throwing away all this old school deep reinforcement learning and then just basically putting LLMs in the loop. And I think it's a beautiful thing because putting LLMs in the loop is actually way easier. Like, you don't need very high level math to understand LLM in the loop, right? Like, you know what I'm saying? You don't need high level math to basically do this. But a lot of deep reinforcement learning is very complicated. It's based on these kind of variants of the Markov decision process, and it's like it can get very complicated very quickly. And that acts as kind of like a gatekeeping mechanism to prevent people from doing RL. But I think that now that you have RL, that's actually very, very easy, because all you're doing is just basically feeding things into an LLM, and the LLM just kind of gives you answers magically, right? And you don't even need to push gradients into this. It's basically zero shot. So I think this is huge because it opens up reinforcement learning to a huge amount of people that maybe couldn't do reinforcement learning before. Low-level actions are hardware dependent, underrepresented. Existing efforts have largely treated LLMs as semantic planners, right? Where the LLM is choosing the activity to do, but then you have to basically human engineered control primitives. And this is something that we saw on the Voyager paper as well in Minecraft, where the LLM is writing code, yes, but the code that it's writing is basically the Minecraft API. So like you have to have an API that actually does things well, such as like, I don't know, like a create pickaxe, like move over here, move over there. So all you got to do is create an API like that allows the robot to be controlled. And then the cool thing is that you have to create an API that is easy for an LLM to use. So it's like, make your robot a tool that the LLM can learn to use. On the other hand, reward functions are shown to be flexible representations that can be optimized for control policies to achieve diverse stacks, while their semantic richness makes them suitable to be specified by LLMs. Yeah, so you don't want to be manually designing reward functions. You want the LLMs to basically design those in language. We introduce a new paradigm that harnesses this realization that by utilizing LLMs to define reward parameters, using reward as an intermediate interface generated by LLMs, we can effectively bridge the gap between high-level language instructions and corrections to low-level robot actions. Mujoko, actually, I think Mujoko recently was either open sourced or acquired. I don't exactly know. It used to be that you had to get licenses, so you couldn't even use Mujoko. You had to go get a license, and then you had to like have this license file. It's like really fucking annoying, but they might have open sourced this. This is the main dev for Mujoko, this guy Yuval Tassa. But I don't know, I'm kind of like split. Like sometimes I think Mujoko is dying and it's basically like on its way out. But then sometimes Mujoko makes a comeback. So I don't know. I'm kind of split on whether or not Mujoko is actually the future or not. But open sourcing it was definitely a good idea. To systematically evaluate the performance, we designed a total of 17 tasks for a simulated quadruped robot and a dexterous manipulator robot. So manipulator robot just means a robot that has an arm and a gripper, and whenever you see that word dexterous in front of it, that means the hand. So let's go to the actual thing here. Right, you see this hand here, which is the simulated shadow hand. Where is it? Right there. So this is called a dexterous hand because it has dexterity, right? It has all the fingers. So that's dexterous manipulator, and then this is a quadruped, right? Everybody knows the quadrupeds. It's basically like the Boston Dynamic dog robots. They basically just have 4 legs. Language to actions, language to code. Yeah, this is the big one. This is some related work. So it like anybody who's kind of been in robotics and reinforcement learning, every single paper that you've read always has a definition of the MDP, right? So it's kind of like if you're in the image generation space and you read a lot of diffusion papers, you end up reading the same explanation of diffusion over and over and over again, right? Because every single paper that does diffusion has to basically explain what diffusion is. And reinforcement learning is also similar, where every single reinforcement learning paper generally had basically this little paragraph right here where they're just going to explain to you what a Markov decision process is, where you have the state, you have the action, you have the reward, you're trying to maximize the sum of the discounted rewards and so on and blah, blah, blah. But like to me, this is the garbage that's going away. I think all this trash, all this MDP, all this unnecessary formalism, and I just feel like that's going to go away, and you're basically just going to have LLMs that just generate code, and the person who is designing that doesn't even know what an MDP is, right? I think that's the future I want. I want a future where like some young engineer is like making crazy awesome AI that runs on a robot, and then you ask them about MDPs, and they're like, what's an MDP, right? I think at that point, that's when we know we've made it as a society. Okay, so you have your actual motion controller, which is going to be your actual low-level C code that actually executes this, right? So your LLM is not going to be fast enough to actually generate actions, right? These robots run at very fast control loops, right? So the motion controller here, this is going to be actually C code. So you're actually going to have C code here that actually runs some kind of PID controller, actually runs some kind of velocity control loop on each of the joints of this robot, right? And that needs to be very, very fast. So people are still going to be writing C code for this, but all of the intelligence is now almost separated from this, right? All of the intelligence is now in this kind of weird natural language space, right? Code space, where the Python, or where the LLM is basically writing this like weird pseudo Python code, which then gets turned into motion commands. Okay, so it looks like they have, similar to the Voyager paper, right? There was basically all this kind of prompt engineering where basically when you're sending the LLM, you're like, okay, you have to use this, you have to have this specific format of things, choose between one of these 4 things. So it's almost like prompt engineering is becoming the new level of complexity, right? Where we got rid of all the complexity around mathematical formalism and reward shaping, but now we have the introduced complexity of actually having to do all this almost like prompt engineering where you're deciding how to prompt and how to basically get the LLM to answer these questions for you, which is kind of interesting. As reward tuning is highly domain-specific and requires expert knowledge, it is unsurprising that LLMs trained on generic language datasets cannot directly generate a reward for specific hardware. I don't think you would want them to generate a reward. I think you want to abstract the whole notion of a reward almost away. You want to make it all just like goals, like a language goal. More concretely, we decompose the problem of language to reward in 2 stages: motion description and reward coding. Okay, so they're basically, unfortunately, the people at DeepMind can't help themselves, and they're gonna over-engineer this and break it up into 2 pieces. They're gonna have an LLM that decides what motions to take, right? Kind of like the action or the policy. And then a LLM that decides the reward, which is going to be analogous to the value function, right? And in a lot of reinforcement learning systems, those 2 things are usually 2 separate neural nets. So you have a neural net, sometimes called the value function, which basically looks at the current state and tells you what the reward for that state is. And then you have a different LLM called the policy, or a different neural network called the policy, and that's the one that actually looks at the environment and then determines the action. So there's a lot of variants of that. There's a million different varieties of value functions and actors and every permutation and combination of that you could think of, but here they're basically having a similar kind of pattern where you have an LLM for each of those. Motion controller needs to map the reward function. Little typo here, there should be a space, to low-level robot actions that maximize the accumulated reward specified by the reward translator. Two simulated robotic systems: quadruped robot, dexterous manipulator. We design a diverse set of tasks for each robot to demonstrate the capability. So what do they have? They have basically different types of pick and place, and this isn't a mobile pick, right? So if you remember in the original Facebook paper, they're doing mobile picks where they move and then pick. this is not a mobile pick. This is a stationary pick. You see the robot is already there. The object is guaranteed to be in reach of the robot. I think this arm is actually called a panda arm. Let me make sure. Panda robot arm. Yeah, this one. These are pretty cool. I got to play with these before, but they basically have like these little buttons on them, and you can like basically program them like almost like in a no-code kind of way. But even more important than that, they have Python APIs, which is great, you know? A lot of industrial robots, like for example, this one is the UR. I think the UR also has a Python API, but Universal Robotics is the company that makes these, and they come in a couple of different sizes. There's small ones and then there's bigger ones. But the companies that make, for example, ABB robot arm, yeah, these arms, these are industrial robot arms. These do not have Python interfaces usually. These are everything is in C, and not only that, but they're made of metal, so you basically have to be super careful because they will crush your arm. No problem, no questions asked. This, like think about this one, this robot arm here, like this thing will straight up fucking kill you. But these little plastic little robot arms like that, you can't. You'd have to try to get injured by these robots. So generally, at this point in most reinforcement learning research, you're not really seeing these type of industrial arms. You're seeing these more human-friendly arms. Okay, what was I even talking about? I guess I was talking about this. Reward coder only, where an LLM directly maps user instructions to reward code instead of going through the motion descriptor. A CODIS policies, where the LLM generates a plan using a set of predefined robot primitive skills instead of reward functions. Okay, so I guess here they're basically saying, okay, well, do you want this to basically be end-to-end, where the LLM is basically deciding everything, or do you want the LLM to merely just give you the reward and then you have maybe a more classic RL on top of that? Reward coder only and code as policies. So I guess they combine both of them. So reward coder only would be value function only. LLM is acting as the value function. Code as policies is LLM is acting as the policy. And then I guess the green one is LLM is acting as both the value function and as the policy. And of course, it kind of makes sense that it would be both of them, or the combination of them that succeeds. Yeah, and another thing to notice here, like for example, look at this, the way that this. So this is one. So earlier I was talking about a rollout or an episode. This is one rollout. So you see, it's roughly 10 seconds, and then once you get to here, the simulation would reset, which means everything would get reset all the way to here, right? And when you're doing this in a computer, that reset is instant, right? You can basically just reset it, and now you're good. Now you can run your policy again. But that's not the case in the real world. If you were to even try to do this in the real world, you see how sloppy it is, where it's just like kind of like slapping against everything. Like, you would break this robot hand in less than like 10 minutes. If you had actually tried to run this policy on a real robot, this exact real robot, you would break this hand, which is like hundreds of thousands of dollars, in 10 minutes. So that's one thing to realize, is that the way that we end up getting humanoid robots is almost guaranteed to be basically trained entirely in simulation, and then just put in the real world, and hopefully you have some combination of domain randomization and simulation and some amount of transfer learning. Maybe they even use things like LoRa's and OFTs like we saw yesterday, but to adapt it to the real world. But any robotic system in the future is, in my opinion, almost guaranteed going to be trained 99% in simulation, just because doing any rollouts or any episodes in the real world is just so much more expensive. Validation on real hardware. So this is kind of interesting too, right? So going to what I'm saying about stories, right? So here you have a paper from DeepMind, right? And DeepMind used to be separate from Google Robotics, Google Brain Robotics, which is where I did a little bit of stuff. I did a little bit of work there, but generally those two used to be pretty separate. And anytime you see kind of generally Mujoko or Sims, generally that tends to be DeepMind. But then here you have Google DeepMind work now suddenly being used on the normal Google robotics, right? The DeepMind people don't really use this robot. So I think this is showing you that there's been an official marriage inside Google. So the DeepMind teams and the original Google Brain teams, which I think is actually called something else now I think they used to be more separate, which is the brief time that I was there is whenever they were separate, but now it seems like they're together. So they've officially merged into one team, right? The fact that this work here, which is DeepMind work, is now being run on this robot, which is probably sitting somewhere in Mountain View, that to me tells me that those groups have merged. Cool. What are we at in terms of time here? Damn, we're at like 1.5 hours. Okay, what else can we talk about? Can we read anything else from this paper? If you guys have any questions, feel free to ask. I feel like I've been just ranting about robots, but keep banana upright. Quadruped robot with 12 degrees of freedom. Dexterous manipulator robot with 27 degrees of freedom. Yeah, 27 is because 20 of those are the actual hand, and then the other 7 are the arm. What else? Evaluation. Make the robot stand upright. Open the drawer. Good. Now put the apple inside the drawer. Good. Now release the apple. Like, this is so powerful. Like, people don't realize just how fucking powerful this is, but we're going to be talking to robots in less than 5 years. You're going to be able to tell the robot in language what you want it to do, right? And I think right now, right, like another thing that I talk about, and a theme that I keep bringing up in some of these streams, is that you see this like kind of like pseudo Python API here, set L2 distance reward, right? It's still the case that the names of these functions and the ordering of these arguments and choosing which ones are keyword arguments, which ones are arguments, and so on, those are all designed for human readability right now, right? It's like whoever picked the name for this picked it so that other human programmers can identify it and use it. And you see how they use things like set and get and so on, because there's kind of historical patterns of naming functions that you want to match to. But once you get to a point where the only like 99% of the use of these types of functions and these APIs is from LLMs, right? So it's actually incredibly rare that a human is ever reading this function, and 99% of the time it's an LLM that's reading this function. I think that's going to change the way that these functions are named, the way that these APIs are designed, the way that you pass in arguments and maybe have defaults for arguments. I think all of that is actually going to change, because we're going to have to design APIs and code such that LLMs are optimally making use of it rather than humans optimally making use of it. And I think that's kind of another pattern that I'm kind of seeing come out of the woodwork that I feel like is pretty interesting, and I don't know, maybe a potential research direction for one of you. Okay, what else do we got? Mujoko, investigate a new paradigm for interfacing with a robot through reward functions. I don't know if this is a new paradigm. I feel like they're a little bit behind the curve. We've seen probably a dozen papers that try to do this. We even saw one out of Google Brain that had this as well. Okay. See if they have anything in the appendices here. You tell the robot this. It's early in the morning. Make the robot head towards the sun. And then normally this would just be absolutely insane that you could turn this into an actual robot command, but LLMs are just so powerful that they can say, okay, I guess that means face the robot to the east. Here you have some kind of prompt engineering here, right, where you're starting to kind of programmatically create these instructions based on objects. Here you have the different functions. Head towards specifies a target heading direction. Walk, forward speed, sideways speed, turning speed. Set joint poses, leg names, joint angles. So this is the actual full prompts. So this actually seems fairly complicated. Look at this. This is the prompt engineering complexity that I'm talking about, where we've gotten rid of some complexity, but now we've introduced all this extra complexity where it's like you need to define what these prompts are. So describe the motion of a dog using the following form. And then here's the description. So that would be basically what this is. Make the robot stand upright on the back feet like two human. The torso of the robot should roll by some number degrees towards the right. The torso should pitch upward at some number degrees. The height of the robot's center of mass or torso should be at something meter. So even here, right, little decisions like, do you use center of mass like spelled out, or do you use COM, right? I wonder if they did an ablation study to decide which tokens should we use here, right? Center of mass or COM. So prompt engineering is actually very complicated if you think about it. There's a lot of potential complexity there. Hello, they call me Ken. Is Galactic related at all to Galactica? I do not think so. I don't know what Galactica is. What is Galactica? Galactica machine learning? Large language model for scientific... Oh, I think we've seen this before. No, it's not at all related to that. It's a framework for robotics and reinforcement learning. Right now we're reading a prompt that is being used on a quadruped. The robot should face. If facing certain direction, it should face. If turning, it should turn at blank. The robot should go to a certain location, move a certain speed. If going to a certain location, moving a certain speed. Optional. Steps on the ground at frequency during the stepping motion. The foot will move. Like, this is kind of intense. If you see phrases, replace the entire phrase with a numerical value. If you see phrases like choice, it means you should replace the entire phrase with the choices listed. Like, this is what you're telling. You're giving the LLM this like fucking gnarly paragraph, and then you're telling it to replace with values. I will tell you a behavior that I want the quadruped, and you will provide the full description of the quadruped motion, even if you may only cheat a few lines. Do not add additional descriptions. Do not explain. Only return the code. Be concise. Use as few bullet points as possible. It's like the robotic prompt engineering is totally going to be a job. It's already a job. Look at this. You have people at DeepMind getting paid to do robotic prompt engineering. Do you really need to import NumPy just to fucking turn a degree into a radian? It's gross. just make this function accept a quarg that says either radians or degrees. And you don't need to waste your tokens importing this. See here, look at this. You're wasting tokens on this NumPy import. You're not even fucking using NumPy here. Ugh. That's another thing too. It's like whenever you're prompt engineering for this, I think that one thing that people don't talk about is the number of tokens. And I think we did this on the little project that we were working on, the Discord bot, the one that I've been working on, right? In one of these streams, actually, we went through here and we changed these prompts. So we were looking at, I think it was maybe this prompt. Yeah, but like, how do you make this prompt less tokens, right? Like you're paying for every single token. So if you can get the same behavior by cutting down on the amount of tokens, you should do that. And I think like too many people, like too many times when I go onto these papers that where they're doing these kind of prompts, it's like they're not paying attention to that. Like, do you really need this many words? Do you need this tokens here? Like, you're just wasting a bunch of tokens to do that? Like, try to make it as concise as possible. Try your best to generate code despite the lack of context. You need to encourage the LLM. Sim to real residual term. To enable successful deployment, we design a regularization term to help achieve steady motions. Oh my god, so this is like the actual reward engineering crap. This looks so gross. You see, so this is like the same kind of twisted logic that I constantly kind of poo-poo all the time, where basically you have to have these very complicated things where it's like, okay, well, we have a second term that regularizes the joint and end effector velocities. We have a third and fourth term that encourages the objects to move slowly. We have more terms that do this and more terms. It's like, I feel like this is all going to go away, right? The LLM is just going to know that. Or you're going to ask the LLM to just give it for you. Dude, this is like, this NumPy is triggering me. Look at how many tokens they wasted just doing that import. But I don't know, maybe to play devil's advocate, maybe by having this import NumPy as NP, you can almost think of it like in context, kind of like almost like a chain of thought. You know what I'm saying? Where you're, by forcing the LLM to write out import NumPy as NP, it like forces it to start thinking about Python and NumPy and you know what I'm saying? So maybe there's a benefit to this import statement, right? Maybe this import statement puts the LLM in the right frame of mind where it automatically starts to interpret this as Python code. Whereas if you didn't have this import, maybe it wouldn't. It would come in here and maybe it would think this is like something else, something maybe not Python, right? So maybe this forces it into Python thinking. Yeah, token cost as a metric. Like here, right? Look at the way that they do this, right? You could probably, the way that this formatting is done, this is for a human, right? Like why, whenever you look at code and you see these kind of matrices that are written out like this, where they're basically, you have each line separately, that's so that a human can see this, right? So me as a human, I look at this and they're all nicely lined up, right? So I can see that 0, 0, 0, 0, 0, and I was like, okay, cool, I see what that matrix is. But an LLM does not care about whether or not these are lined up. The LLM is reading this token by token. So if I was trying to be very efficient with the amount of tokens I would use, I would get rid of the new line here. There's a new line token there. There's a tab token here, potentially 4 spaces tokens, right? And LLMs inefficient with tokens, Python. I think I reposted one of these on my Twitter. Let me see if I can find it. My account. I'm trying to find a specific thing. Sorry, guys. No, I don't know if I don't know if I can find it, but like someone posted something that made it very clear that it's actually not even, sometimes there's not even a tab token. It's actually 4 space tokens, which is even worse, right? So there's the new line token, then space token, space token, space token, space token, bracket token, 0 token, comma token, space token. So just think of how many tokens they wasted by putting it in this way. Same thing here. What? Hashtag Python? Okay. Pretty cool. I think that's pretty much it, guys. I don't know. I'm gonna go do something else, but maybe we can do a little summary here. So today we looked at 2 different papers. We looked at a paper called Galactic, which comes out of Meta, and it's a simulation and embodied AI framework that kind of extends the Habitat 2.0, and really kind of from what we were seeing, it's really just Habitat 3.0. I think the main thing it does is it basically runs the physics in a CPU thread so that you don't need to use the GPU to do it, even though I feel like most people use the CPU or physics on the CPU. But there was a couple things that, or a couple people that were trying to do the physics on the GPU. They batch more cleverly, so they're batching the rendering by basically sharing the textures and the meshes so that they don't need to basically have multiple simulation instances that basically duplicate the same information. Unfortunately, they are still using very old, it's not very old, it's just only like 5 years old, but the reinforcement learning that they're doing is very ancient here. They have a ResNet 18, LSTMs, small LSTMs, so that's not great, you know. This is kind of stuck in the past. And then we reviewed a paper that has a more modern type of reinforcement learning, which is just now starting to become a thing, which is this idea of LLMs kind of in the loop, right? And I think this is much more promising. I think this is the future of reinforcement learning. And it's basically this idea where the LLM writes the code, and then you just have these code is just basically low-level motion controller C code, right? And what else? What else did we find out? I think one thing that we saw is that there's basically this whole new field that has opened up of robotic prompt engineering, which is basically how do I design these prompts that I'm feeding into the robot in order to pick specific actions and then run those low-level commands. And from what we've been looking at, these prompts are still very primitive. Like, they're not necessarily taking into account tokens. There's certainly no kind of chain of thought in here, right? It's basically you just give the entire prompt and it gives an answer. Like, there's probably opportunity here to do some kind of chain of thought, maybe some kind of retrieval situation going on if you want to be extra fancy. So yeah, there's still room to improve there. Even the stuff that we saw for the Minecraft was more advanced than this, you know, so sometimes even if you come from a super fancy institution, right, like this is like a paper from DeepMind with like 20 people's names on it, and the techniques and the prompting that they're doing is more primitive than a Voyager paper. Yeah, it's like half the amount of people, and they're doing more complicated things. These guys even had a kind of a retrieval type of mechanism where they have this kind of like library of skills, and then they retrieve the skills from this library, and they're searching this library with embeddings. Like, this is already more complicated and advanced than what they're doing here in this paper. This is still very simple. But yeah, that's maybe a review, and then maybe a tease about what reinforcement learning and robotics is going to look like in the future. So definitely a very interesting time to be in the robotics world. So there's kind of an explosion of these startups, especially in the humanoid space, right? So I really like this one, the Digit Robot. Yeah, this is my favorite humanoid robot, but you have all these different companies working on it, right? Bunch of different startups. Pretty much all the big tech companies are doing their own version of it. You have Tesla kind of joining this race as well. So a lot of opportunity. I think there's going to be a lot of jobs. There's going to be a lot of progress. And I don't know, maybe we have humanoid robots by 2030. I feel like that's not even that crazy anymore. It used to be crazy to think about humanoid robots in your house, but I feel like if I had to bet money on it, I feel like by 2030 you can probably buy something that looks a little bit like this, probably costs like $20,000, and you can speak to it in natural language, and it'll do simple things like move your dishes, or I don't know, something like that. Figure, is this another one? Sure, all right, but here's the thing though, right? Look at the duplicate. Here's how you can tell. Like, you have to, people are cherry picking, right? So look at this, right? You see this? You can't fake this. You can't fake these little robots walking around. But when I go to this page, what do I see? Stationary, still frame. Weird generic graphic that doesn't have any meaning, right? So like, if these guys were actually as advanced as these guys, they'd have a demo like this, right? They'd have videos of their robots working, but you don't see that. You just see a bunch of like potential, like, look at this, like a guy moving sideways, like. So I don't know, don't trust these companies, because the VC world is basically a Ponzi scheme, and your ability to raise money is not necessarily tied to the quality of your product. And a lot of times when you're in a hot space like humanoid robotics is now, you can raise a bunch of money on a story. And these people, it looks to me like all they have is a story. Like, yeah, these graphics are great. Yeah, you paid some guy $10,000 to make very cool quality graphics for you, but where is the actual robot? Where is the video of the robot actually out doing things in the real world? If you actually had a robot that worked, you would be showing it, but you don't, which means that you don't have a robot that works, right? It's the age-old cherry-picking Ponzi scheme situation, but I don't know. We'll see. I'll leave it at that. Who knows? Maybe one of you guys can go into these companies and actually get them to actually do the LLMs. And I think it's actually very great, because it's kind of what I was saying. I feel like old school reinforcement learning, there was a gatekeeping that occurred there, because the math that you needed, the statistics that you needed was pretty intense. And so it was very difficult to come in as someone who maybe only knows a little bit of Python and like actually do things. But this new type of reinforcement learning that's based around LLMs and prompt engineering, you don't need to be very good at math to be good at this, right? And I feel like there's going to be kind of a renaissance where I feel like all these people are going to come in here and they're going to learn how to do this way better than some crusty like PhD guy who like knows all about PPO and A3C and all these different things, but like the guy who just sits there and just like throws Python around and very, very quickly does some prompt engineering, like that person's going to make more progress. So I don't know, just maybe predicting the future there, but maybe I'm wrong. I'll leave it there, guys. Hope you have a happy and joyous weekend. Feel free to like and subscribe, join the Discord, recommend papers. If not, have a great time, and see you guys later.